Hi, I'm going to do the example problems at the end of class 11 notes. So let's start out here. We have in this example here, an unaccommodated hyperopic eye is represented by a plus 57 thin lens. So I'll start by drawing myself a little picture. P equals plus 57 diopters, and the far point is located 33 centimeters. So there's a far point over here. Okay, so it asks, what is the lens-retina distance? So somewhere in here there's a retina. So let's apply V equals U plus P to that situation. And we're going to say we've got an object at the far point. Of course, in the case of a hyperope, this is a virtual object. So there are rays that are entering the lens, converging towards the far point. So we can just put that information in there. So the object divergence is this 1 over 0.333, and it's a positive value. And the power of the eye is 57 diopters. So this is 3 plus 57 equals 60 diopters. And then that means that the distance itself is 1 over that divergence, 1 over 60 diopters, so that's our friend, the 1.667 centimeters. Part B asks us, what is the amount of accommodation that will allow objects at infinity to be focused on the retina? Again, we'll apply the divergence equation, only now our object is going to be at infinity, so it's the object divergence for something at infinity. And then the power is now the power of the eye plus some accommodated power. But remember, our image divergence is still the same as it was before, so we know that that's this 60 diopter number over here. And of course, the divergence of an object at infinity is just 0. So we're going to have that the accommodated power is the image divergence minus the eye power. So that was 60 diopters minus 57. And so we've got that the accommodated power is plus 3 diopters. That's how much accommodated power they need in order to see something at distance. And we should recognize that that is also just equal to the far point divergence. And that makes sense because, remember, the far point divergence is sort of the amount of hyperopia. It's the amount of correction that the patient needs. And the hyperopes can basically self-correct by doing accommodating. So in some sense, this is also the contact lens correction, because we can use that rule that the contact lens correction is equal to the far point divergence, right? And they're just doing their own correction by accommodating instead of actually wearing a contact lens. Okay, and part C, what accommodation do we need to see objects at 50 centimeters? In front of the eye. So again, we can apply our V equals U plus P, and now we're going to be using a U of minus 0.5, and the P again is the P of the eye plus P accommodating, and V was that plus 60 that we had before, and so the accommodation power is going to be plus 60 diopters minus the power of the eye, which was 57, and then plus this quantity here, right, that's minus 2 diopters itself, right, 1 over minus a half. And so when I move that to the other side, that's going to become positive 2 diopters. And so that works out to be 5 diopters. Okay, and again, does that make sense? We'll compare that to our earlier calculation. In order to see an object at infinity, we needed to have an accommodation of 3 diopters. And now in order to see a real object 50 centimeters in front of the eye is going to require even more accommodation, so plus 5 diopters. Good, so that makes sense. Okay, so now let's do the second example, which is problem 6.3 from Keating. So it says we have an unaccommodated eye represented by a plus 60D thin lens. So let's put that in here. And we've got a lens to retina distance of 16 millimeters, so 1.6 centimeters, and they have an accommodated power, a maximum accommodation of 8.5 diopters. And we're supposed to find the far point and the near point. Okay, so let's start out with far point. So V equals U far point plus power of the eye. And so we can solve for the far point divergence, being image divergence minus the power of the eye. And that will be 1 over 0.016 is 60. So this is 62.5 diopters minus 60 diopters. So that's plus 2.5 diopters. And so I'm going to remind myself, in case this is useful down the road, that this image divergence here is plus 62.5 diopters. Okay, so we've located the far point. We've got a positive sign here. So that's telling us that the far point is over here somewhere. How far is it? The far point location would be 1 over 2.5, and that corresponds to 40 centimeters. All right, and that's telling us, so the positive sign is telling us that the far point is over here downstream from the eye, and so that corresponds to hyperopia. This is a hyperopic eye. And now we need to find our near point. So again, we'll use our divergence equation, and we're going to be locating the object distance, the object divergence for the near point, and so that means we're going to be doing our accommodating. We just rearrange this to solve for the near point divergence. All right, so our image divergence, as we had from before, is this plus 62.5 diopters, and then we subtract the power of the eye, and then we also subtract our accommodated power, which was this 8.5 diopters. And that is minus 6 diopters. And that means that the near point distance is 1 over the divergence is 1/6 minus 16.7 centimeters. So in our figure up here, that minus sign, right, that minus sign there is telling us it's a real object location, so it's somewhere upstream from the lens. So the near point distance is minus 16.7 centimeters. Okay, so now it asks us to find the correction for a contact lens and then for a spectacle lens. So we know that the contact lens correction is just the divergence of the far point. And if we look back here, we see that our far point divergence was plus 2.5 diopters. All right, so we know that the contact lens is going to be plus 2.5 diopters, which is appropriate for the hyperope that we said this was. Okay, I've resketched the figure for this eye from our figure up above. So we've got the eye lens and the retina, and the far point located over here, 40 centimeters from the lens of the eye. And then I put in our spectacle lens here, a distance of 1.5 centimeters upstream from the eye. And we're supposed to find the power of the spectacle. So what power of spectacle lens placed at a distance of 1.5 centimeters will correct this vision? And the key to doing these kinds of problems is to remember that we have to have the focal length of the correction lens has to equal the distance from the lens to the far point. So on my picture up here, that's the distance from the spectacle lens all the way over here to the far point, right? And so that's the distance that needs to be the focal length of our spectacle lens. And so just looking at the picture, I can see that what that distance is it's the far point distance plus this extra d here. So the focal length of my spectacle lens must be the far point distance, which was 40 centimeters, plus this d, which is 1.5, so this is 41.5 centimeters. And so then the power of the spectacle is just 1 over the focal length, so 1 over 0.415, 2.4 diopters. Now, plus right? So I'm figuring out the lengths, how big this length was, what was the focal length, just by looking at my picture. From the picture, I can see that that distance measured from the spectacle lens to the far point is a positive quantity. And that goes along with this sign here, which is also consistent with a hyperope. We know this is a hyperopic eye, so we need to correct it with a positive lens. So that's where that sign comes from. It's interesting to compare this spectacle lens, which was shifted by 1.5 centimeters from the eye, right? That resulted in a 2.4 diopter power. And the contact lens was 2.5 diopters. So number one, it fits our expectation that for a hyperope, as you move towards the spectacle lens, you reduce the power that's necessary. But also notice that if you've only got a 2 diopter correction, then the difference between the contact lens and the spectacle lens is pretty small. It's not even a 1/4 diopter. The difference becomes more important if the correction itself is larger. So if you have a 5D hyperope or a 7D hyperope, then this difference can be more noticeable. Okay, so now let's do the last example here. And this is problem 6.4 from Keating. All right, so we've got an eye that has a plus 60D lens, and it has a screen to, or a lens to retina distance. Right, we have an accommodative power of plus 2.5 diopters. All right, so we're going to do the usual thing, finding far points and near points. So let's find the far point. We use the divergence equation, V equals U far point plus P. So the far point divergence is the image divergence minus the power of the eye. And this is 1 over lens to retina distance and minus 60 diopters. And this is plus 58.1 diopters minus 60 minus 1.86 diopters. All right, so what does that mean? So we can locate the far point, 1 over minus 1.86. So we get a far point distance of minus 53.76 centimeters, not diopters, centimeters. The minus sign on the far point divergence is telling us that this is a myope, right? Far point is somewhere upstream from the eye, and that's consistent with a myope. Okay, so now let's find the near point. Again, we're going to use divergence equation, be locating the near point object divergence. And when we do that, we will be accommodating, so we have both the power of the eye and the power of combination. So the near point divergence is going to be our image divergence minus the power of the eye minus the accommodating power. And that gives us this number plus 58.1 minus the power of the eye minus the accommodating. And so it gives us, for the divergence of the near point, a value of minus 4.4 diopters, and that corresponds to a near point location of 22.7 centimeters, negative 22.7 centimeters. Right? And so the negative is also telling us that it's a distance upstream, so it's somewhere up here. And we notice that the near point distance, 22.7 centimeters, is less than the far point distance. So again, that's consistent. That makes sense. This is a myope. So they have a far point out here, and then a near point is a little bit closer. Okay, and now let's calculate what the spectacle lens power needs to be to correct this patient. So I've drawn in the spectacle lens here. I've recopied our figure from above for our eye, and showing our far point over here. Because again, I'm going to remind you that what we need to do here is we need to find the focal length of the spectacle lens, and that has to be the distance from the spectacle lens to the far point. And so that's why I like to draw these pictures, so I can see really, really clearly what that distance is in my model. And so we should also add here the distance d that we've separated these by. So this is 1.5 centimeters. And so looking at my figure, I can see that the focal length of my spectacle lens needs to be the distance to the far point minus this d value. And so then going back here and looking at that, so the far point distance was 53.76. 53.76 centimeters. And I'm going to subtract from that 1.5 centimeters. And so that means my focal length is 52.26 centimeters. And so then the power of the spectacles needs to be 1 over that. And so that results in a power of 1.9 diopters. Now I need to look at my figure and think about, should that be a positive power or a negative power? And looking at my figure, I can see that this focal length I've drawn here from the lens to the far point, right, which means, remember, why are we doing that? It's because this location is also the secondary focal point for the correction lens. And so I'm drawing this focal length from the spectacle lens to its focal point, and that's an upstream distance, and that means that this lens, contrary to the way I've drawn it, is a negative lens, a diverging lens, right? Because that lens has its secondary focal point on the same side of the lens as the object, the direction the light's coming from left to right. So I know that this power down here needs to be a negative power, just to be consistent with my picture. And of course, that's also consistent with, we classified this eye as a myope, and so we know we're correcting myopes with negative powers. And we could compare the spectacle power to the contact lens correction power, which I didn't do yet, but we know that the contact lens that you need to correct it is just equal to the far point divergence. And if we look up here, our far point divergence was this number right here, minus 1.86 diopters. So let's write that down here, minus 1.86 diopters. And so we see, does that make sense? So the spectacle lens is showing up at a slightly larger value than the contact lens. And that's the correct situation for a myope, so that as you move the correction lens closer and closer to the far point, this focal length is getting smaller, and so the power needs to be getting bigger. And again, you see it's not a very big difference, and that's because the overall correction is quite small here. It's only 2 diopters. But it gives you a sense of numerically the difference that a small vertex difference would have in the power. Okay, I think that is all of the questions we were asked to do here.